Good afternoon, everyone. My name is Sai Aditya Pradeep, and I'm the Scientific Program Manager for AIM EFRC. And we're all here today as part of this particular webinar series to witness a talk by Dr. Ghosh. But before we get into that, wanted to go over a couple of programs that are sponsoring these particular webinars. Um, First one is the first one is AIM EFRC. So EFRC is an Energy Frontier Research Center, and the mission for AIM is to build an AI-enabled inverse design approach for fundamentally understanding and integrating material manufacturing design of advanced polymer composites. Next, we have the IDEA's NSF NRT, which is a traineeship that focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, advanced composites, and sustainable manufacturing. And lastly, we have the SAMPI Baltimore Washington chapter, which is part of SAMPI, that is an international professional member society that provides information on new materials and processing technologies through technical presentations like these, and they also have a journal, among other things. This particular season of the AIM Technical Webinar Series is focused on technical talks by distinguished researchers at the cutting edge of composites, AI, and manufacturing. And with that, I would like to request our Associate Director, Dr. Gangli, to introduce our speaker for today.
Thank you, Sai. Good afternoon, everyone. My name is Gangli. I'm a professor of mechanical engineering at Clemson University. It's my pleasure to introduce Professor Somnath Ghosh to this who is a speaker of this webinar. Excuse me. Professor Somnath Ghosh is the Michael G. Callas Chair Professor in the Department of Civil and Systems Engineering and a Professor of Mechanical Engineering and Material Science and Engineering at Johns Hopkins University. He is the founding director of the JHU Center for Integrated Structure, Materials Modeling and Simulation. He is currently the co-director of NASA STRI Institute for Model-Based Qualification and Certification of Additive Manufacturing, and was the director and the PI of the Air Force Center of Excellence in Integrated Materials Modeling. His research focuses on multiscale structure materials analysis and simulations, multiphysics modeling and simulation of multifunctional materials, materials characterization, process modeling, and emerging fields like integrated computational materials engineering. The topic of Dr. Ghosh's talk today is modeling damage in piezocomposites, a digital twin approach. Dr. Ghosh, it's all yours.
Thank you very much, Professor Lee. Okay.
Sorry, Dr. Ghosh. Before we hand it over, just wanted to acknowledge that this particular webinar series is brought to you by the Artificial Intelligent Manufacturing Paradigm EFRC Center that's funded by the Department of Energy under this particular award number, as well as the National Science Foundation Research Traineeship, which is the Inverse Design Training in Advanced and Sustainable Composites under this particular award number. We have reoccurring webinars every month, and we will have our final talk next month. So details will be out on social media soon. And with that, just wanted to hand it over to Dr. Ghosh. Thank you for this. Yeah.
Thank you very much for this invitation. It's an honor to present in this forum. Today, as the topic suggests, I'm going to be talking about a modeling approach which involves both physics-based modeling and machine learning to probe into the multi-scale nature of damage evolution in piezocomposites. Now, while I say this is piezocomposites, the framework that we are going to develop or propose, it is applicable to a large variety of different materials, including regular composites, polymer matrix composites, for example, or even metals. Okay, And I'm going to kind of generalize the overall idea so that one can take this framework and develop other, develop extreme detection of extreme value problems in different types of materials. As Professor Lee said, I am actually co-directing a NASA STRI on developing a digital twin for additively manufactured materials. And many of you working in that field may know that one of the major problems there is QNC, qualification and certification, because of the nature of the difficulties in the predictability of damage, example, fatigue, and other things. And this particular framework that I'm going to be showing here for Piezocomposites, we are also trying to build that for additively manufactured materials. But I'm not going to be talking about that in this. So I want to acknowledge my two ex-students, Dr. Preetham Tarafdar and Dr. Saikat Dan, who has contributed significantly, and my current postdoc, Dr. Yang Liu, who is currently working on the various aspects of the machine learning based digital twin. Okay. I want to acknowledge AFOSR, Mechanics of Multifunctional Materials and Microsystems program, who has sponsored most of this work. So the first thing I want to talk about is the multiscale multiphysics phenomena of damage and failure in composites. So here we have some armor applications, okay, and as you can see, this is a structure that is made of glass, carbon fiber, epoxy woven composites. So this is, if I look under the microscope, I do see the woven microstructure here. Okay, these are mesoscale yarns in epoxy matrix, and then within each of these yarns, I see intra-yarn fiber matrix composites, and typically when you have damage, the damage starts, so high strain rate damage initiates in the microstructure and propagates through the scales to cause the failure of the overall structure. This is at the macroscopic scales. So this is a phenomena of multiple scales involved in the damage process. What I'm going to be actually mostly focusing today is on this non-destructive evaluation of evolving damage sensing in structural components. For example, this is an aircraft for which, let's say this is made of a composite. Typically, the failure or the damage process starts deep down in the microstructure in the form of, could be fiber breakage, matrix cracking, and so on. And then it moves up the scales to manifest as the overall failure of the overall structure. Now, typically, different NDE techniques have been used. For example, this shows a built-in sensor network involving actuation and measurement. Okay, so this consists of a sensor network together with a diagnostic hardware and analysis software. And this other one corresponds to sensor data acquired through eddy currents. And typically what happens is these sensor signals are processed in a posteriori fashion. That means after the operation. External sensors are typically attached to the host surface that identify predominantly surface damage, and therefore we have limited damage sensing at the hotspots, which could be deep down in the microstructure somewhere. So the objectives of model-based predictive platforms for composite structures and materials, there are multiple prongs in those objectives. The first is multi-scale damage evolution and composite structures with multi-level and mesostructural linkages exist in these evolutions. The next one is that ubiquitous damage sensing is necessary, especially subsurface at the source, because by the time damage manifests at the surface, it may have already grown to failure. And the third objective of these model-based platforms is to understand the evolving phenomena such that one can facilitate location-specific material and especially microstructure design. Now, this corresponds to a multi-scale predictive platform. This is a pure predicting platform that I'm talking about for damage evolution in fiber reinforced woven composite structures. So like I showed before, this corresponds to a woven composite plate under ballistic impact. Actually, we worked on this together with Army researchers who were working at the University of Delaware at that time. So in the mesoscale, this corresponds to the evolution of mesoscopic damage in the woven RVE. And if I look further down, I see this corresponds to the matrix with matrix damage. And then there are these fiber yarns. Okay. All right. And then if I look inside of these yarns, I do see this fiber matrix composite microstructure, and actually the damage is starting through mechanisms of matrix cracking, interfacial debonding and such at this scale. So the link between these scales is very important, because one really needs to connect the lower scale damage phenomena or damage and failure phenomena or lower scale damage phenomena to the failure phenomena that's happening at the higher scales. The next one is this virtual damage sensing digital twin for the piezocomposite that couples multi-scale modeling together with machine learning in order to probe the early stages of the crack, okay, which could be happening because of loading, it could be happening because of fatigue damage, and so on. So this corresponds to the microstructure. And this is the structure itself. So the structure itself has a representation of the damage. And if I have an electrical field there because of the piezocomposites, we have in the microstructure coupled electromechanical and damage fields here. So these are piezoelectric fibers embedded in a passive matrix. You have these electrical fields and mechanical fields and damage fields, which is happening at the microstructure. That manifests as upscaled electromechanical damage fields. And then one can then probe into those damage fields to see, what kind of microstructural evolution is happening locally. Okay. Now, in order to get a fast, full field prediction, full field reconstruction of this coupled electromechanical damage fields, it's a good idea to incorporate machine learning, because machine learning has various good attributes of developing these fast, efficient surrogate models. So we can use certain machine learning techniques, and I'm going to go into that in details. Okay, here I'm showing a neural operator for damage sensing that can clearly show the full field development, and then from there we can then zoom in locally to see the evolution of the microstructural variables, state variables, for example, the deformation, the fracture, as well as the electrical fields. Now, when you connect these multiple scales, typically various homogenization methods have been used, and many of them suffer from a number of disadvantages. For example, many of them are not suitable for complex nonlinear material behavior. For example, anisotropy, tension, compression, asymmetry, that is typical for many of these materials, especially under fatigue load. History and path dependence. Many of them are computationally prohibitive for large-scale structural simulations, do not explicitly represent lower-scale descriptors in higher-scale models. Machine learning-based surrogate models typically need large data sets, large uncertainties, and there is a lack of interpretability. Now, today there are scientific machine learning methods which include physics-based constraints. However, many of them still suffer from the difficulty to capture history dependence. A desirable alternative is to upscale constitutive models, which are low dimensional, that are thermodynamically consistent with lower scale models. And machine learning is used to derive coefficients of these thermodynamically consistent upscale models in terms of lower scale parameters. So it makes these coefficients interpretable in terms of the lower scale parameters. And this is something we have been working on. So it's called parametrically upscale constitutive models, or PUCMs. This is machine learning enabled physics-based parametrically upscale models. They represent higher scale constitutive models that are thermodynamically consistent with lower scale model responses for dissipative irreversible processes with explicit parametric representation of lower scale morphology. It could be, for example, crystallography or general morphological descriptors, okay? And we will call them ramps. So this is a canonical form. Now, the overall form, including the set of higher scale state variables, for example, all of these, strain rates, the work, the damage work, temperature dependence, that evolve with deformation and failure are governed by the second law. For example, one can use the Helmholtz free energy and minimize it to obtain this form. But this is more important here. The constitutive coefficients here are coefficients of internal variables. These are internal variables that are functions of lower scale descriptors. And when I say lower scale descriptors, these I'm going to be addressing them as representative aggregated microstructural parameters. We will call them ramps. Okay, so the ramps represent lower scale descriptors, and I'm going to give an example of this. And this part is governed by the first law. So here, to build the parametrically upscaled coupled constitutive damage mechanics models, what we need first is we need to identify the ramps, the representative aggregated microstructural parameters. And also we need to, corresponding to given microstructural RVEs or statistically equivalent RVEs, we need to create a microscale response database, which can come from micromechanical modeling. And we will be using this data together with machine learning, for example, using genetic programming based symbolic regression or ANN techniques to generate these higher scale constitutive coefficients. The constitutive law itself is set by thermodynamical equivalence or consistency, but the coefficients, the parameters, instead of doing an inverse analysis from experiments, we are now going to use machine learning to develop functional forms of these constitutive coefficients in terms of the ramps representing the lower scale material descriptors. So the advantages are machine learning tools create physics-informed constitutive parameters as functions of lower scale descriptors, making them interpretable. Much smaller database because of thermodynamically bound windows is required for training these constitutive parameters, readily incorporated in commercial codes. As a matter of fact, we've been distributing some of our models through these UMATs to our industrial collaborators. Reduced number of variables make them several order of magnitude more efficient, but with very comparable accuracy. So now to build this, it's a two-way approach. The first is the bottom-up. This is the hierarchical. So we start with the micromechanical models. We identify the micromechanical regions, statistically equivalent RV regions. We identify the ramps, okay, and I'm going to talk about that, as well as we use these micromechanical models for generating the MRDB, the micromechanical response database. Then we use machine learning to come up with these parametrically upscale models. Once we have that, those parametrically upscale models can be used to generate training data for my machine learning based, and I'm going to use two types of machine learning. One corresponds to the LSTM methods, the other one corresponds to these neural operators, okay, to basically predict the full field. I'm going to be predicting the full field state variables. This correspond to mechanical, electrical, as well as damage variables throughout the the domain, computational domain, using these neural operators. And from that information, then I can zoom in to generate my microstructural, damage fields or electrical fields. And the important thing here is I'm going to be placing equivalent sensors, okay? Sensors, these correspond, for example, in this case, it can correspond to the electrical field measurements at selected points on the surface. And we have developed a genetic algorithms-based sensor network optimization tool to generate the optimal location and numbers of these sensors. So from a limited number of sensors, then we can generate the full field state variables in the computational domain. So that's the top-down macro to micro analysis. So the first part is to focus on the generation of this PUCCDM. I'm going to try to move through this a little fast because it's quite elaborate, this process. So this is the generation of these methods. So we first, from the microstructure, we do characterization and data generation method. Okay. From that, we generate the ramps, the representative aggregated microstructural parameters. And then we also generate this, from the evolution of, deformation, damage and electrical fields, we generate this microstructural response database. And then we use data-driven techniques plus thermodynamics. Okay, the data-driven techniques will be necessary for my machine learning techniques to operate on that, to generate this PUCCDM constitutive coefficients. And then based on that, we will have the PUCCDM constitutive models that can be inserted in any structural analysis, to actually do the structural level analysis with direct linkages to the microstructure. So the advantages are the data-driven methods with thermodynamic principles are used to bridge material length scales, efficient microstructure descriptors in the form of ramps for the microstructure database, homogenized micromechanical response database for machine learning to operate on. The constitutive framework is governed by thermodynamic principles, and then evaluate the PUCCDM constitutive parameters as function of ramps using supervised machine learning techniques. So a little bit about the micromechanical analysis. The micromechanics, as you can understand, consists of the fibers or multiple phases, the fibers in, let's say, a polymeric matrix. And in this particular problem, I'm modeling it as an elastic, finite deformation elastic matrix material. okay, so this is for the mechanical problem. For the electrical problem, we have electrical fields associated with large strains, and damage due to electromechanical states are because of, interfacial debonding, fiber breakage, matrix cracking, as well as for the electrical field, we have an energetically consistent electrical crack face condition here, where the electrical field can permeate through the medium in the crack gap. We use a phase field model. Okay, a phase field model is a regularization of the sharp crack. Okay, and this is the regularization, as you can see. The advantage of the phase field model for modeling matrix cracking, as well as this cohesive zone-based phase field model of the fiber matrix interface, in the matrix, it implicitly tracks the crack path, eliminates the need to introduce cohesive elements in the general matrix, and electrical crack phase condition can be incorporated using the phase field order parameter. And then the other advantage of the phase field is that I can introduce interfaces using the phase field, the other order parameter. One is the order parameter S, which is used for modeling matrix cracking. This is a regularized matrix, a diffuse crack. And this is a diffuse interpretation of the interface that I'm using my variable eta in order to represent. So the eta variable is going to represent my interfaces corresponding to the fiber matrix interface. These are some of the kinematics that represent the both the deformation as well as the gap opening due to interfacial decohesion here. Okay, I don't have time to go into this. These are the governing equations. There are three types of governing equations. One is the balance of linear momentum, or the equilibrium equation corresponding to the displacement field. These are all for finite deformation. As you can see, finite deformation, damage field, and it is also coupling the electrical field. The electrical potential field is represented by the Gauss law, and the phase field balance equations correspond to the damage field in the microstructure, also representing the interfacial debonding. Now, the coupled finite deformation damage evolution model is also represented by a constitutive model, which is given by the Gibbs free energy density function for a degrading piezoelectric material with interfaces. So this corresponds to the Gibbs free energy for the piezoelectric fibers. Okay, it corresponds to elastic energy, the piezoelectric energy, the electrical energy, and also the crack energy, both in the fiber and in the dielectric matrix. Okay, the important thing is that the elastic energy also corresponds to tension compression asymmetry, and here the tensile part is actually degrading with the evolution of the order parameter S that corresponds to the cracking, the fracture in the matrix material here. This corresponds to the piezoelectric energy density, the electric energy density, and this corresponds to the crack surface energy density. The first term here that you see, this corresponds to the matrix energy density, and the last part corresponds to the interfacial energy density. And here with the identification of these eta corresponding to the interface, we can introduce the cohesive potential and the capacitor energy because of the electrical fields into this crack energy. Okay, you can see some of our publications on this for more details. And then the eventual constitutive relations can be derived from the Gibbs free energy in the following form. The first one corresponds to the mechanical constitutive law. The second one corresponds to the electrical field constitutive law, and the last two corresponds to the crack energy, the internal microforce and the power conjugate. So this is a coupled way of solving the, this coupled model, the multiphysics model, coupling mechanical, electrical, and damage fields. Now, I want to emphasize that, by doing a cohesive interface modeling of the phase field, okay, we are able to reproduce or replicate experimental observations where, we see, for a model like this, this basically consists of one fiber here. It's constrained like this, and we are applying a loading. This is just a mechanical loading. Experiments here have shown, just a minute. Okay. Experiments in this paper have shown that the crack, the interfacial decohesion is not symmetric, okay? And what you see is if you use just a phase field model, you would get a symmetric crack propagation, prediction. On the other hand, if you incorporate this phase field based interfacial debonding together with the cohesive model, you do see the evolution of the cohesive zone at the interface, which is not symmetric. And this actually matches the experiments quite well. So here is a model of micromechanical simulations for a 1,3 piezoelectric composite. Okay, here you have an epoxy matrix, piezoelectric fibers, PZT5Al. And here we are applying both a mechanical load as well as an electrical load. And here you see the evolution of the matrix cracking together with interfacial debonding in the microstructure. And because of the energetically consistent crack face condition, you also see this localization of the electric field in the microstructure. And the crack patterns from successive debonding and matrix cracking is shown here. So that up to that point was a micromechanical model. Now we are going to develop the upscale model, the PUCCDM. So for that we need the identification of the ramps, okay, from microstructural characterization. We need to establish the volume average response database from microscale analysis followed by homogenization. And then we need to use machine learning using these two data together with the thermodynamical framework to actually map the ramps to the calibrated parameters. Okay, so the first step is this corresponds to the microstructure. This is an experimental micrograph that we are characterizing using the 2-point correlation function, okay, S2, okay, which produces this high dimensional data. This S2 is the probability that you have if you put a position vector here, a vector here, the probability that the head and the tail of the vector R are in the same phase. That is literally the meaning. It consists of, it contains anisotropy, distance, and size distributions, and two-phase microstructure specified by 2-point correlation functions. It's a fairly good representation of these two-phase microstructures. But these 2-point correlation functions generally correspond to high-dimensional data. So to reduce that, we do this principal component analysis, where here you can see it's basically reducing this high-dimensional space into a space that corresponds to the eigenvectors of the covariance matrix, these are the V's, together with the alphas which correspond to the principal components. So these are the principal components of that analysis with the leading eigenvalues. And we take only a certain number of these principal components. As you can see here, the total variance decreases with the increasing number of principal components. And after that, the higher order PCAs don't participate much in representing the variance. So therefore, we kind of truncate after a certain number of principal components. But together with this, we also have an uncertainty quantification to see the effect of this truncation on the overall behavior. You can see this corresponds to the original S2 function, and this is the reconstructed using the PCAs. So the ramps here correspond to the fiber volume fraction as well as the PCA represented S2. These are the alphas. Now, the thermodynamically consistent PUCCDM framework consists of the Gibbs free energy representation. Now, the only thing is, now we are representing a homogenized upscale representation. So rather than individually representing or resolving each of the cracks, we represent the aggregated effect in the form of a damage mechanics law. So we have the stored elastic energy representing the aggregate of the microstructural elastic deformation. Then we have the stored piezoelectric energy density. Again, this is an aggregate, and which is actually kind of reducing because of the increase of the damage because of the microstructural cracks evolving. Then we have the stored electric energy density and the damage energy density. And then we form the constitutive relations in form of this upscaled Gibbs free energy form. And then we have the damage potential function representing the onset of the overall damage corresponding to the microstructural damage evolution. Okay, and this corresponds to a Kuhn-Tucker condition corresponding to the irreversibility of the damage evolution. Now, what you see here, these are the parameters in the PUCCDM models that you can see here are represented by the red the color. These are the parameters. But these parameters will be now represented in terms of the lower scale ramps, which now correspond to the fiber volume fraction as well as the principal components representing the distributions. Okay. To do that, there's a two-step process. First is we set up the PUCCDM parameters from the MRDB using the code Optuna. And here we are minimizing the error in the macroscopic load, the electric load, as well as these correspond to the damage evolution. And then once we have that, then we use this artificial neural network to come up with a representation of those various parameters, the PUCCDM parameters, in terms of the underlying microstructural ramps. Okay, so this corresponds to the fiber volume fraction, and this one is a function here. This W is a function of the principal components representing the distributions. With that, then now corresponding to each microstructure, we can then actually have a pure macroscopic evolution. Here we are showing the evolution at the macro scale associated with the damage evolution. That means this is the evolution of cracks in the microstructure, and this corresponds to the evolution of the principal damage components in the macrostructure, as well as the evolution of the electrical field. Okay. Just to show the influence, the strong influence of the microstructure on the macro scale response is realized through these PUCCDM simulations. Okay, and this corresponds, what you see here is the force displacement behavior corresponding to different microstructural, the representative volume elements. And you see the volume fraction affects both the elastic and the damage behavior, but for the same volume fraction, microstructural volume fraction, just having different distributions affect the overall damage response. Okay, This corresponds to the mechanical field. This corresponds to the electrical field. Okay. And this is very important if you want to introduce this location-specific materials design to improve the damage characteristics of the overall structure. Now, I don't have time to go into this, but we have coupled this entire framework with the UQ framework, uncertainty quantification, that takes care of three uncertainties: the epistemic uncertainty of microstructure characteristic model reduction error, also the epistemic uncertainty of neural network based model reduction error, and then the aleatoric uncertainty of inherent microstructural variability. Okay, so all three of them. And these correspond to the outcome of this uncertainty quantified PUCCDM models. Okay, and you can see this right on the left side is the evolution of the crack, okay, with loading. This corresponds to the element stress component together with, this one is the stress component for the mean plus minus the variance here that you are seeing for the different stress components. Okay, and this corresponds to the underlying microstructural damage evolution. Okay, this corresponds to the matrix damage as well as the interfacial debonding. Okay, now we go to the last part of this discussion, is to develop this virtual damage sensing digital twin. As I said, we will use two types of techniques, machine learning techniques. These are supervised machine learning techniques to predict the full field state variables from limited surface-based measurements. Okay, so here I'm talking about this geometry-informed neural operators, but also we have this LSTM-based models. Okay, so the problem statement is, given a set of spatially distributed ramps, okay, given by this, and electrical signals measured at a finite set of surface locations, like you see 1, 2, 3, 4, these are surface locations, predict the damage evolution in the microstructure at a macroscopic location of interest. Okay, so at any given location of interest, can I actually predict just from these few surface-based sensors? So these are the measurement of the electrical field as a function of time at different at the different sensors as a function of time. And correspondingly, these are layers that are represented by different ramps corresponding to different microstructures that you're seeing here. The ramp field in the PUCCDM framework provides a constraint relation to avoid non-uniqueness. If you don't have enough these ramp gradients, then you need a lot more of these surface-based sensors in order to provide uniqueness in the predictions. Okay, so the key characteristics of the machine learning model is local macroscopic damage state at a material point is strongly related to the micromechanical and electrical fields in its neighborhood. The path dependency is evolution of damage state is dependent on the history of the mechanical and electrical fields, and this is very important. So there are three of these macroscopic fields that we are going to actually probe as full field variables. One is the damage indicator. ID equal to 0 corresponds to intact state. ID equal to 1 is a damage state. Deformation gradient as well as the electrical field. So the first we tried this conv LSTM, where the electrical signals at the sensors together with the ramp field are inputs to this convolutional long short-term memory network, corresponds to the convolutional neural network and recurrent neural networks. Okay, and from here you get the deformation field, the electrical field, and the damage indicators in the entire. This is the full field representation of the macroscopic responses. And once we know that, we can identify the hotspots, and from there we can solve the micromechanical problem to get the microstructural damage evolution. This is the architecture, so we have this ANN with the electrical signals to output homogenized electrical field, and that is coupled with this convolution with the ramp distributions, okay, for learning the non-local features, which is then used with the LSTM network, for the output response quantities. So this corresponds to the learning history dependence. Okay. An alternative technique is the Fourier neural operators. This is FNO-based damage sensing. This is the neural operator which actually maps this input field. Okay, the input field, as I said, consists of your electrical measurements at selected surface locations, as well as the ramp input field. And the output field corresponds to all the state variables that I talked about in the entire domain. And this corresponds to the architecture. Okay, F corresponds to the Fourier transform. Okay, so you have a lifting operator given by P, okay, and then followed by a nonlinear operator layer in the latent space using the Fourier network here, and then the latent field back to the output space given by this operator Q. The advantage of the FNO-based models is that it gives a universal, it maps between infinite dimensional function spaces, so it actually has a universal approximation of continuous functions, as well as it is discretization invariant. Okay, that means it doesn't depend on the grid that you're training this network on. So if you have various types of geometries, you can couple this FNO with graph neural operators to create your geno or geometry informed neural operators that maps any given domain onto a regular periodic domain for the FNO layers, and then you do this inverse mapping to generate the variables in the actual domain. So these are the three inputs. These are the ramp fields, the electrical signal, and sensor layout. Then you use the FNO-based neural operators to map the response fields, the full field of the response. And then once we have that, we can then use the damage fields together with the micromechanical simulations to probe the microstructural damage evolution. Okay. So this is a rectangular panel. This corresponds to the ramp field, the ramp fibers representing different microstructures. This corresponds to a sensor layout for the panel with 5 sensors. And this corresponds to the evolution of the electrical field at those 5 sensor locations. Okay. And then this is a comparison of the FNO-based predictions to the ground truth model, which corresponds to the PUCCDM-based FE simulation results. So the top part here corresponds to the ground truth, and the bottom part corresponds to the predicted fields, the full fields, by the FNO based calculations. Okay, and you can see for a very small fraction of the time, even I have to say the PUCCDM based finite element models are pretty fast compared to having to do explicit micromechanical analysis. This is very fast, but obviously if you can get the FNO based predictions, it is much faster. And then we identify a location of interest at which we can recreate the microstructure to recreate. This corresponds to the mechanical field, the displacement field, and this corresponds to the damage evolution in the microstructure. Okay. This is a comparison of the FNO and Cornwell STM. As you can see, these are predictions. This is the ground truth relations, prediction by the Cornwell STM and predictions by the FNO. For the Cornwell STM, there are significant errors which particularly near the surface, okay, because of the sparse surface measurements. On the other hand, because we are modeling, mapping between infinite spaces for the FNO, in this case, the error is very small. And this one you can see, this is a comparison of the relative error as a function of time at a given location of interest. The blue one here corresponds to the Cornwell STM. The red one here corresponds to the FNO. If we move from a panel to a domain here with 16, this is an airfoil structure with 16 sensors. This corresponds to the evolution of the electrical field at those sensors. And then corresponding to that, we have here the evolution of the electrical field, the deformation field, and the damage field, a comparison between the ground truth and the FNO predicted models. Okay. The last thing here is we also have coupled this analysis with a genetic algorithm-based optimal sensor layout schema, where you can train this genetic algorithm using basically the placement. This is a sensor grid on the top surface, and these are some of the sensor layouts, and you can basically use this GA to come up with a loss function that corresponds to the difference between the ground truth and the predicted values corresponding to different sensor layouts to give the optimal behavior. So these are some of the sensor layouts for the panel, and this corresponds to some of the sensor layouts for the airfoil structure. Okay, I'm going to stop now. So this is the summary. So we believe that we have built a novel virtual damage sensor coupling highly efficient physics-based modeling with machine learning for piezocomposites with strong correlation between the damage and electrical fields. This interface is virtual full field predictions from limited surface mounted real sensors. A unique deep learning architecture using FNO is used to correlate spatial and temporally varying electrical fields to damage states. Ramps are necessary for unique predictions, and these are important translatable tools with implications in location-specific design. Current steps that are being taken to develop this VDS virtual damage sensor digital twin for arbitrary loadings and geometries, and incorporating the UQ in the framework, and then extending this platform to other materials. I think with that, I would like to stop. Thank you.